Putala, good morning. Can you hear me?
Yes, sir.
Okay, very good. Very good. So 1029. Normally, if you are facing some power interruptions, there may not be full participation, but I would like to know the number in general if there is number in general joining the Zoom these days. Any idea? How many students are there joining Zoom sessions normally? Per batch? 50%? 70-80%? Any idea? But hope many can join. And also I just want to remind you that you should join this Google Classroom. That is very important. Okay, joining the Google Classroom is extremely important.
Excuse me, sir.
Yeah, Bhutan.
Sir, lecture video එක sir දාන්නේ මේ Google Classroom එකටද? YouTube එකේ.
No, as usual, man email karna pata. Google Classroom දාන්නේ මම exercises. We have to do some exercises this time to drill the subject. That's why. So some assignments. So I will post into the Google Classroom. But normal videos I will post you as usual. Yeah. Normal videos I will post you as usual. So today we only have 2 hours. So shall we start? And today 29 April 2022 Thermodynamics. So welcome all the 3 batches, manufacturing, mechatronics and BST. 2020 semester 2 B1. So today we are going to learn about a phenomena called flashing. Okay, these are very important phenomena. Flashing, this phenomenon is flashing. So we will understand flashing, and our focus is how we can utilize flashing in cooling technologies. Okay, without understanding this, you will not get the real technology unless you have understanding of this. Okay, flashing. Before going for flashing, let me not to remind, but let me suggest you to download the software. This is not about flashing. CoolPack. CoolPack. TAK, if I'm not mistaken. This is from the University DTU. Okay, CoolPack. I think it is COOL. Yeah, EACK pack. Okay? From DTU, Denmark Technological University. This is quite famous software. We can have a lot of data. It's a database. CoolPack from DTU. Okay. So you better download this CoolPack from DTU. If I need to put the link for this, if I need to put a link, you can look for that. CoolPack. Software, this is a free download. CoolPack. So you go for the university website, DTU. Don't go for other websites. GTU. You can browse it. I'm browsing for you here. Maybe Bhutali, you can explore it. But anyway, let me share with you the Coolpack software. It is something like this. It is something like this. So you can explore this. So this goes to this. And let me put the screenshot. From here, you can look for a lot of data. So if we look into the types of, we call refrigerants, later we are going to learn about this. So you can see a list, even the latest refrigerants, even CO2, water, ammonia, nitrogen, oxygen, all the data, the two-phase. Okay, saturated properties you can see here, and also there are a lot of data. So if you need to look into, let's see, R1348, you just click this, you will get the data. Okay. So at pressure 0.516 bar, what's the temperature of this two-phase liquid? Okay. So you can get this data. So the very important thing is only just attending the lectures will not help you that much. Okay. So it is very important to explore the subject, explore the applications. It is very important because this is one of the very important subjects, and just 40 hours teaching, you will not get this to the fullest. Yeah, but this is extremely important subject. So I recommend you to download this Coolpack software or database so that it's easier for you to look into the information. Even you can draw some graphs as well. See the data, the graphs also you can look, even you can draw the curves here. This all from the ASHRAE tables, they somehow they have an interface. So they do this representation. Even we can do some graphs. Yeah, draw. Even you can have some graphs as well. So if you look into that again, so you need to draw graphs. Still you can try maybe. Okay, you can try drawing graphs as well. Okay, so that's about Coolpack. So you can see here, top left, see Coolpack, the symbol here, the icon, Coolpack. So hope you can recognize this. Hope you can recognize this. You can download the latest version of this. Huh? Okay. Not this icon for the simple cool pack. Okay, good. So later we will be using this software as well for some of our analysis because it's convenient. Huh? Good. So let's go back to flashing. Flashing. So flashing, this is connected with liquid. Okay, this is connected with liquid. This is not about solid or gas. Let's see, this is connected with liquid. Okay, flashing connected with liquid. So in flashing, liquid turns fully or partially into gas. So this is the story, okay? In flashing.
Excuse me, sir.
Oh, can't you see
Sir,
this?
sound එක ගොඩක් අඩුයිනේ sir.
Sorry, Buta?
Sir, sound එක ගොඩක් අඩුයිනේ sir. ශබ්දය ඇහෙනවා අඩුයි sir. ඒකයි.
Okay, okay. Buta දැන් ඇහෙනවද? ඒත් නැත්ද?
දැන් හරි sir.
චුට්ටක් ඉන්න බලන්න let me just phone the solution. පොඩ්ඩක් ඉන්න. සද්ද ඇහෙනව මදිනේ. දැන් කොහොමද?
දැන් හොඳයි sir.
Now okay, sir.
දැන් හරිද පුතා? චුට්ටක් ඉන්න බලන්න.
හරි sir.
පුතා ඇහෙනවද දැන්? හරි.
දැන් හරි sir.
දැන් හරිනේ හරි. Thank you very much for your cooperation. Really appreciate it. ඇහෙනවද? ඇහෙනවද පුතා? Hello? ඇහෙනවද?
දැන් ඇහෙනවා සර්.
ඔව් සර්.
සද්ද නම් පොඩ්ඩක් වැඩි සර්. හරි සර්.
ඇහෙනවනේ. හරි. දැන් ඇහෙනවනේ නේද? හරි. ඇහෙනවනේ පුතාලා? Okay.
ඔව් සර්.
හරි. ඇහෙන්නේ නැත්තම් කියන්න. So in flashing, liquid turns fully or partially into gas. In flashing, liquid turns fully or partially into gas. Okay. So we will try to understand this. With some examples. Okay, with some examples. Okay. A frying pan. Okay. A frying pan. This one. So if this frying pan is hot, okay, if this frying pan is hot, frying. කට්ටියගේ පොඩි device එකකින් උනත් පේනව නේද මේක? It's hot. Let's see. If this frying pan is hot, let's imagine when you pour oil, you will hear a noise. Okay, you will hear a noise. If this pan is hot enough, okay, is hot enough or hot, let's say, is hot. Later we will talk about the temperatures. It's hot. When you pour oil, okay, onto the pan, you will hear a noise. Yeah. So that is flashing. That is flashing. Yeah. There some oil turns into, not to say just vapor form, but some oil turns into vapor or gas. Partially. Okay, the portion of there, some oil, let's say, portion of oil, a part of oil. Oil turns into vapor or gas. Okay. If it's too hot, if it's further hot, or if it's too hot, or hotter, let's say, hotter, maybe 100% turning into gas. Okay. 100% turning into gas. Just imagine. If it's too hot, so hot. Normally before flashing, you used to put the veggies or whatever to be fried. If it's too hot, once you pour oil, P-O-U-R, pour oil, too hot enough, let's say. Once you pour oil, there will be a sudden fire. Okay, sudden fire. Because sometimes when the chefs, they practice cooking, sometimes you can see fire in the oil. Some art of cooking, I don't know. There could be even fire in the oil, I don't know. But there is a possibility. There is a possibility. So oil is considered a fuel type, but we are not talking about fuels here. So for fuels, there is a term you should know if you are going to explore about fuel has flash point. Okay, fuel has flash point. At the flash point, the fuel turns into gas. This is the minimum. And then so we talk about fire. Even fuel has fire point. Okay. And even fuel has another temperature, let's say, not up to flashing or the sudden turning into this moderately hot, let's say. It's moderately hot. We don't know how moderate. So if the frying pan is hot, maybe oil boils. Okay, boils. It is slow evaporation, which means for fuel, even you can have boiling points. It's very important boiling point because sometimes for the freezing temperatures, some fuel or even oil, you may not know there can be even the properties can be changed. Okay, that would be an issue. So you have to explore this, okay, beyond the words, because these are words, but practically you should have some good sense of boiling, flashing, and even firing, okay, cold fire. So we are not going to talk about oil, but we are interested on this flash point, okay. But our application is not about using of fire. Our application, as I mentioned, we are looking into cooling technologies, but we should start from something known, okay, this flashing. So flashing has some risk, okay. There are safety issues, so you should be aware of this. So we will look for one more example for flashing. Imagine if you pour petrol, what happens? Instead of coconut oil, at that temperature, if you pour petrol, it's a disaster, okay, sudden fire, okay. So oil boiling points, even well below that may be the petrol flash point, okay. So very important to understand this boiling points, flash points, fire points, and there can be some others as well. So even for the fuel oils, the fuels, lubricants, so there are this nature of temperature depending situations, okay? So you have to explore this, okay. It is very important to explore, okay. It is very important to explore. And now I'm talking not about this. Let's say so if you cannot hear again, just let me know. So experimentally, even you can find the data, the boiling points, flash points, fire points for different pressures, because it depends on pressure as well. So let's say this is a hot plate. Okay, hot plate. Okay. Hot plate. Very interesting phenomena. One time learning, let's say at high temperature. We don't know how high, okay? But I would say here, you have to imagine, let's say I'm dripping this is a water droplet dripping on the plate. So once this hit the plate, this water droplet, once this hit the plate, at no time this get flattened immediately. At no time. It means this is sudden. And after that, immediately, this turns into gas or vapor very fast. That is the flash. Even in the camera, flash means it's a sudden light. Okay, sudden light. Light appears for a millisecond and disappears. Just a flash only. Okay. So here also, what happens is when this plate is quite hot, this water droplet turns into a huge cloud of vapor. Let me tell you the size, okay? Let me tell you the size of this, okay? Turns into huge cloud of vapor. I hope you can see it without, in your small devices even. Yes. So now, not the frying pan, this hot plate. Hot plate. Sometimes you are using to bake roti or roti kuchane, and also hot plate. If temperature just at maybe 100, water boils. What has boiled? So this hot plate now is, let's say, moderately hot. It flashes. Okay, flash point. It flashes, but maybe partially. Sometimes partially because it absorbs some heat, this droplet, and partially flash point, but maybe flashing, maybe partial. So here, water, portion of water turns into vapor, so it is flashing. If it is very hot, maybe 100%. Not to say very hot, or if it has a sizable heat supply, uninterrupted heat supply, then maybe continuous, means suddenly all the liquid turns into 100% vapor. Just imagine, no much argument, just imagine. 100% turning into gas. Okay, means no more liquid, superheated, but for water, fire is not relevant. Fire is not relevant. If it's too hot, maybe 100% turning into gas. Or superheated. Okay, superheated. But in flashing, the vapor and liquid both are there. Okay, vapor and liquid both are there. Just imagine. So volume of this and volume of this. This volume is almost 1,000 times. Believe me. That's how this flashing makes the volume quite bigger when it turns into gas. Okay? 1,000 times. If a tiny droplet of liquid turns into vapor, get flash, volume is almost 1000 times. Let's say if it is gas, really 1000 times. So vapor, we can get the values later. Let's say 1000 times. Okay, yeah, like at this scale, 1000 times is the scale. Okay, this is the scale. Let's say, okay, almost 1000 times. So you imagine the volume. Now another application, not to say application, another scenario I'm taking before going into cooling applications. Flashing. Let's say safety concerns. Okay, safety concerns. Safety concerns. So let's say now we have 78, very good. But in the Google Classroom, Putana, I noticed that only 60 students. So you should join the Google Classroom, please. Huh? You should join the Google Classroom. This is a human. Part is here. So we all are like this. And our body is 80% water. Our body is 80% water. The balance mostly the skeletal part and some other elements maybe. Okay, but 80% is H2O. Okay, and other maybe elements and some bones, all the balance 20%. So I think I may be correct. Imagine Imagine. So if this body suddenly exposed to steam, suddenly exposed to superheated steam, exposed to highly intense means highly intense means very high heat source. So this is highly intense means very high temperature heat source, and a bigger heat source, like let's say sometimes the bursting of boilers, sometimes exposing to the steam. What happens? This body, it is same like this water, at least superficially. It's the same phenomena takes place. So your all water here, at least at the skin level and deep inside, there could be flashing effect. So what happens afterward? What happens afterward? If that is the case, what will be the consequence? What will be the consequence? The person disappears. Okay? Only the skeleton remains. That's why. So this can be explained from flashing. No time. Okay? This is the worst case, but this is possible. So steam exposed into the steam boil accidents, sometimes the fire accidents. Okay, fire accidents. Normally in the fire you see the charred body. Okay, but if the fire is so high, so heavy, you may see this nature of things. Example, in bomb blasts. You know, bomb blast means it's heavy. At the vicinity of the bomb blast, okay, it's an intense heat in huge amounts. Bomb blast or the blasts. See, intense and good enough, big enough to engulf. Okay, so what happens is even this disappears in no time. Okay, that's why there are persons can be missing. Okay, so the reason is this sudden. evaporation of water, and finally, no person is there. Okay, so industrial accidents, you should be extremely careful. Never ever get exposed to, of course, that is not possible. Even it is never take any risk in the field when you are dealing with thermal sources. Okay, that is very dangerous. Okay, so precautions very important, and upfront knowledge of this very important. So I believe this is unforgettable knowledge you have learned from these technologies, that the flashing, the risk factors in flashing. Okay, so that is risky. So what happens really is this heat energizes the water molecules. That's the point. The heat energizes the molecules, and then molecules becomes more independent, and then they will be apart. Means flesh, blood, all will be disappeared. Yeah. Because molecules become more active. Okay, that's all. So active portion of molecules, so getting away from the liquid and turns it to gas in no time. Okay, good. So පුතාලා ඇහෙනවද කියනේවා? ඇහෙනවද?
Yes, sir.
Okay, very good. So this is one time knowledge, you will never learn this. Huh? So this is the time you have learned this. So always we have this risk. So this is the issue. Even recently, I think generator, small generator, I think it may be the engine blast, engine connected to a generator blast, and a mother and a daughter died because of that accident. So what is that accident? The fire. Okay, fire, and other than the fire, the shock. Shock also can make these molecules energized. Okay, the shock, the fire and shock, considered deadly. So safety should not be compromised. Your safety and the others' safety, because you are knowledgeable. So others may not have this knowledge, so they will not foresee this. They have no idea. So you are responsible for the others as well. Okay, that is very important. So imagine for a kettle water, even a skin burn, you know the severity of this. So imagine a huge fire like the boil accidents and all. So no chance for survival at all. Okay, good. So let's go to the subject. Of course, this is very important. So since I feel that I should share this with you, that's why I share this, even though not much related to what we are going to learn, but these are related to life. Okay, good. Now we will go for different flash. So 11:18, yes, we have more than 1 hour, enough to learn together flashing for cooling technologies. Okay, I need to draw something here, because later you are going to learn cooling technologies. So you have to use a lot of common sense for these cases. You have to imagine, you have to use your common sense. That is very important. Even animals, they have common sense. So humans, they have some special senses, imagination especially, but of course for animals, we also have very specific senses. Some senses are better than humans. So even animals are different. Yes. This is something like a letter H with a gap here. But actually this is a pipe. Okay, this is a pipe. It's a piece of pipe. A piece of pipe, and here in the middle, so you will see a plate. You will see a plate. On the plate, there is a tiny hole. So how tiny depends on the application. Okay, so depends on the design. Okay, meant for that application. Very interesting. Yes. Too big. This is not a pinhole, but this is a carefully designed hole here. So I make it. What I will do is group it and I will make it. Yes. So this is the one. So here some liquid here, some liquid. Now this is one-time learning. Yes, so you try to understand this. If you don't understand this, probably you may miss this one. Yeah? Some liquid up front. So here liquid. let's see here liquid. And then that makes it unfilled. Okay, here is liquid. Then what we are trying is Anadhutala, I know. Okay, we are going to suck from here, suck the liquid. Okay, we are going to suck this. Okay, suck this. Suck the liquid from the other side of the hole. Okay, tiny hole. So this is a small hole. Okay, this is not a pinhole, but anyway, I will use the word pinhole to show it is this pinhole, let's say, side of the pinholes are there. Anyway, I will put pinhole. Suck the liquid. Okay, suck the liquid. Maybe we use a pump or whatever, we can suck this. Okay, you can imagine. When you suck this, what happens is when you suck this, what happens is liquid comes here. when you suck. See. Liquid comes. Not only the liquids. So there comes some vapor as well. There comes some vapor as well. So this is the situation. Okay, this is the situation. So if I take this, for the continuous, let's say there is sufficient enough. So you can see this. Liquid and vapor.
So excuse me, sir. Sound off, sir.
Sound not off. Can you hear me?
Now here, sir.
Okay. Okay. Very good. Thank you. Very good. So this is the situation of this coming out. See, like this. When you suck, it is like this. But originally like this, originally like this, turns into this. This is the situation. You sum this. So here, what happens is pressure reduced. Pressure reduced. So when the pressure reduced, significantly, pressure reduced. So pressure reduced. Pressure reduced. Now we have to look into some more. So I take this. Because of the suction, what happens? Due to suction. Okay, due to suction. Because of this tiny pinhole, pressure reduced significantly. Pressure reduced significantly. That's a point. Okay. That's a point. Let's say this is water. Looking for water data from this. Water is in refrigeration. This is R71. So now let's say the temperature now in the sense, let's say pressure reduced. Give me a second. Okay. Pressure reduced significantly. Let's say originally this pressure is I will put the pressure here. Atmospheric, or let's say 1 bar. Yes. Do you know the pressure? Unit bar means what? Okay. So you have to explore over there. And now let's say this pressure reduced to 0.5. 0.5. Okay. Pressure reduced to 0.5. Now the situation is like, of course, this one. If you take this, if I further develop this, it is something like this. You have here a liquid portion. And another vapor portion to be this one. You can see like that. So vapor I put this. Liquid. Vapor. Yes. So partially flash. So pressure is 0.5. So two phase. So naturally, you know this vapor means more energized. Okay, listen well, Putha. Listen well. Vapor is more energized relative to liquid. From where this energy received from vapor? From liquid. As a result, when liquid release energy, the temperature drops. That doesn't mean the vapor temperature goes high. No. Temperature drops and part of the liquid energy taken by the liquid itself, a portion of liquid itself, and turn into it. Yes. So this vapor or energized liquid turns into vapor, that energy is taken from the liquid itself. As a result, de-energized liquid means temperature drops. That's how it happens, the temperature drops. So now we will look into this P at 1 bar and P at 0.5 bar, where we are going to look here. So P at 1 bar. Okay, P at 1 bar, but this is room temperature, because this is only the liquid, no vapor. This is room temperature, at room temperature. Let's say room temperature is 25 degrees Celsius. Utala, somehow you have to understand this, what I'm telling. So now here, because this is only liquid, if both liquid and vapor, it's a different story. Okay, this is only liquid. Only liquid. Okay. So here, P at 0.5 bar, two phase. Two phase. What's the temperature? So two phase, you have to go for the steam tables. If you go for the steam table, Rogers and Mayhew steam table, I think I have shared with you. You can look into the same. So now I am looking for 0.5 bar. Oh. No, I will go for further lower to make it practical. Okay, to make it practical. So I will go for lower temperatures. So let's say 0.0 0.01 bar. Okay, 0.01 bar. Two phase. So is 1 bar, so this is reduced a lot. So what's the temperature now? What's the temperature? So this is water. You can go to the table, saturated values for water. So pressure drops to 0.01 bar. So 0.01, you can see 7 degrees Celsius. That's why sometimes we need data. So to be realistic, I take here 0.0. So water temperature become 7 degrees Celsius. Degrees Celsius. Water. And this is water. Okay, this is water. So 0.01 bar, 7 degrees Celsius. So these are natural phenomena. Okay. Temperature. So initially 25 drops to 7. Means cool enough to make the things cool. Maybe air. Okay, in air conditioning, maybe water cool. There are technologies, of course. Now, the technologies are coming using water for refrigeration. Okay, there are technologies are coming. Interesting. So then, if we have this technology, we can apply. So what is the function? Flash. Somehow you have to digest this. So I will take another. Let's say not water. You know some refrigerators, air conditioners, R134A, you have heard of this. If R134A, pressure 0.01 bar is quite low. But let's say temperature for some low pressures, so I will go back to the database. I will go for R134 here. You can see we cannot make it bigger anymore. See R134 here. Okay. So we have the data. Now you can see. I will take pressure. Zero point 888. 0.8. Just imagination, sir. Now this is R134. Pressure is 0.88. Because selecting refrigerants, it's a different story. We are going to learn more. Because we are learning only flashing now. Okay. Let's say 0.88. Now temperature is minus 29. See? Because together existing, okay, together existing liquid and vapor. Definitely. So this the pressure reduced to 0.888. Previous one is 0.01 bar. Okay. 0.01 bar. Now the temperature is minus 29. So cool enough to make the things, not to say cool, freeze. See, when you flash, different type of liquids. When you flash under different pressures, when you flash down to certain different pressures, you can see vapor liquid, two-phase substance of the same originally liquid, but now vapor and liquid together, different temperatures and quite low temperatures. Okay, so now say 0.888 R134 is minus 29, but 0.01 is very low pressure. Water is only 7. That's why water cannot be used for low temperature applications. So these are high temperature applications, high temperature cooling applications. Good. So R134, pressure is 0.8. Let's say this R134A, if you bring the pressure to almost 2 bar, let's say 2.007, because more easier to bring this to 2.007 pressure drop. This is absolute. Yeah, Pita? Okay. So if this pressure becomes 2.007, temperature is minus 10. So I take this R134A, 2.007. So temperature is minus 10. So cool enough to make things. So shall we take up to minus 15? Yes, maybe 1.647 bar. 1.647. So temperature is minus 15. So cool enough to make things, not freeze, but cool or freeze. But here, not deep freeze. Okay, not deep freeze. How to say? Deep freeze means normally below minus 18. That's why I put. But cool and freeze. So this is something like medium temperature cooling. So minus 15 is medium temperature. Minus 29 is low temperature. Applications. Okay. So this is medium temperature applications. 7 degree means high temperature applications. Normally for cooling applications. Cooling applications. So there are high temperature applications. Also, there are medium temperature applications. And there are low temperature applications. Okay. And now let's say in our example, low temperature is -29 here. The pressure is 0.888 bar, low temperature. Medium temperature -15. Pressure is pressure is 1.647. Pressure is 1.647 bar. So R134A1. And high temperature application, let's say this is 7. So I will go for the same refrigerant. 7 is, yeah, it's 7. Pressure is 746 bar. Same. R134A. It's a substance. That's all you can know. Okay. It can be liquid or vapor phase. So temperature is 3.746. Sorry, pressure 3.746. Bar. Okay. Then I will go here. So pressure is 3.746. R134A flashing. R134A flashing. So you flash to low levels, you can see. Okay. Good. Try to understand, Putha. This is an LPG, the gas cylinder. See, pressurized, then only you can maintain this as liquid. This is an LPG gas cylinder. You know, eh? This is R134 gas cylinder, means at normal temperatures, at our temperatures, this R134 is in gas form. That's why we have to keep this pressurized when the temperature is at our normal temperature conditions, like let's say 25 degrees Celsius. So we have to keep this under high pressure. So this is considered a lower pressure for R134. R134A. You can send the attendance also. You can send the attendance. This is R134A. Let's see our temperature. Room temperature is 30. R134A, what's the pressure? So 30. To maintain vapor and liquid, you have to have 7 bar. See here. 7 7 bar. LPG may have 5 bars. So 7 bar to here. 3.746 bar pressure reductions. So you can see. So I have to do some little. So this is R134A. So P at 7 bar. At 25, let's say P at 7 bar for this case. At 30 degrees C. 7 bar. So here, not to say, but here, just we are taking the liquid only. Because vapor comes pass through here, no flash. So here only liquid we check. You can send that in answer. So 7 bar 30 R134A Good. So originally at 7 bar. That's why I changed this 7 bar. So let me summarize this now. In this way, Bhutana. So we are learning flashing. So this flashing can be any type of liquid, not to say any, but there are functional liquids. So here for cooling applications, those could be any this type of liquid identified as a refrigerant, including water. Okay. So initially in liquid form, when you suck it, turn into low pressure and then low temperature, and also part turn into vapor, so vapor and liquid become the phase, two phase. So different substance or the cooling substance, the different substance for different pressures, pressure reductions, there could be different temperatures. Okay. Example, let's say here R134A, we take, so if R134A, (30°C) liquid, it should be pressurized, 7 bar. Okay, so at 7 bar this liquid, and also there can be vapor here, but here by right should be liquid only here. And then when we suck this liquid through this tiny hole, this flash, that's the word, means partially turns into vapor, and this becomes two-phase. This becomes two-phase. Okay, and then pressure reduced. That is depends on our power of suction. Power of suction and the size of this pinhole, this pressure can be reduced. Okay, pressure can be lowered. So there can be pressure levels according to the power of suction and the type of liquids. So somehow you have low temperature now. So that's it. I hope you can understand the practical aspects of this. And for different pressure levels, for different substances, okay, different pressure levels, different substances, when that is in two-phase, same like steam table, saturated water and steam table, so you can have saturated vapor and liquid table, saturated values. So this is for R134. Okay, so you can see temperature pressure drops to 1.647, two-phase. So temperature turns into -50, cool. Okay, so we can use this coolness for different temperature applications, of course, once this is flash. So flashing is very important. Okay, good. And in refrigeration, you should learn this, especially for BST and mechatronics. This is the last chance you are having. So for refrigeration and air conditioning, if you think of cooling technologies, the most popular is,
excuse me sir.
sorry Buddha?
Sir, slide එක share කරලා නැහැ නේ sir.
Sorry Buddha. Okay. Now can you see?
Yes sir.
Okay, very good. So if you think of refrigeration and air conditioning technologies, so the cooling technologies, the most popular we call vapor compression refrigeration. And in this vapor compression refrigeration, without this flashing phenomena. Okay. So here, because of the suction effect, the vapor compression refrigeration without having this flashing phenomena, it is not possible. Okay, that's why. And if you don't have this knowledge of this, you cannot understand what physically and technologically taking place in this cooling technologies. So it is very important to understand this, what's happening. Okay, what's happening. So in industries, to make this flashing in the cooling systems, okay, there are specific components two specific components. One we call capillary. Okay, capillary tubes in refrigeration we are using for this flashing. So later you have to design this as well. So capillary tubes we are using. So let me try to put a picture here for capillary. Even later you should be able to design the capillaries as well. So let me put a simple picture here. Capillary means it's a longer tube with a very small diameter, the fraction of millimeters even possible. Capillaries. So this is we call capillary. And also there could be expansion valves. Expansion means the liquid expands and turns into vapor, a portion. The expansion valves. I will just put a picture. So capillary expansion valve all have very precise arrangements to function in the cooling systems. So this is a key. Expansion valve and capillaries, either expansion valve or the capillary. So where this flashing takes place, okay, flashing takes place. So either expansion valve or the capillary. So what makes suction? What makes suction? So let me put a picture here. Later we will be learning on this. So yeah, you can see a brand always, okay. So this one, this inside is a piston cylinder arrangement, and also there is an electric motor. When this turns, one side, especially this side, this sucks. Okay, this sucks. But before sucks, applying cooling means we have another device here where we extract cooling. So we extract the coldness in this flashed liquid. All this. Okay. So this machine sucks here. Through this equipment meant for extracting coldness. And then pump here. Okay. Pump here. Pump here. And then actually this make sure that. So when you suck here, this is all gas. Okay, all gas. Later I'm going to explain this. Then when you pump here, so this turns, converting into high pressure liquid, because this needs liquid. This flashing effect needs liquid. Okay, so converting into high pressure means you have to compress this. So that's why we call this compression. Compressor. I'm going to teach you all afterward. Compression. So this is high pressure, high temperature line here. Let's see further. Good. So This also high pressure, but still warmer temperatures. And finally, this is liquid, all comes, get flash, okay, get flash. So let me do one thing. I take this out, all out. Connect this to this. So corresponding, there are 4 major components. So suction is being done by this machine. We call this compressor, but this sucks and pump into high pressures. So 4 components are there. Later we will be discussing this, but today we only learn flashing. Flashing is very important. Without knowledge of flashing, you cannot learn. Cooling technologies, that is not possible. Just putting one.
Right. This is a
Expansion valve. Expansion valve. Or even can be a capillary. Flashing takes place. Very critical component. This flashing of this liquid turns into low pressure, low temperature liquid and vapor. But of course, then this liquid contains a lot of coldness, and that coldness makes the application, the cooling application, and finally some evaporated, okay, later we will discuss this, evaporated gas goes to compression. So compression sucks from this side and send the compressed gas here, and finally liquid comes here. Here very important to have fully liquid, because if gas is here, gas won't flash. So you must have liquid here. That's why in this flashing device, a liquid seal is a must. See the hole here, pinhole is sealed with liquid. So liquid seal is a must. Okay. Liquid seal. You can see. Liquid seal. See the liquid seal. It's a must. Okay. I hope you can understand this. Up to certain levels, you can imagine this. It's a liquid seal. extremely hot. Without liquid seal, flashing will not take place. It is very important because otherwise vapor simply pass through. Okay, good. So that's all for today. Not to say a tough lesson, but flashing phenomena. It is very important. Try to understand this. Okay, so download Coolpack, very important. So have in handy that database, very important, and learning of flashing, safety aspects. So this should be an unforgettable lesson for you. Very important for the preventions. Then comes for the cooling technologies, liquid flashing. Pressure reduced. So sudden reduction of pressure just before passing the hall, high pressure. Once the other side pass through, very low pressure. Sudden pressure reduction you see here. But in capillaries may be gradual, but pressure reduced significantly. As a result, portion of liquid turns into vapor. So not only low pressure, the temperature also reduced. That is the cooling application. Okay, good, Putana. So I believe, not to say a tough lesson, because you learn something extra other than flashing, connecting this to cooling application. So try your best to explore this. So I will send this note right now for you to look into. Okay, so look for literature, understand this. Cooling technologies is a very important area. Even flashing, there could be high temperature applications as well. So learn this. Once you learn this phenomena, once you realize that there is a phenomena like this, later we will go for further analysis. Okay, because this is very important. So any questions with that? Tika kari therunane today. Common. Good. So next week, so we will look into cooling applications. So this is cooling system schematic. Okay, good. Today is 29 April. So please join the Google Classroom. Please join. That is very important. So I'm going to email the note right now. Good. Today not. Daily note. Daily note. As usual, flashing. Understanding flashing. Flashing. Cooling applications. And safety aspects. So what's the BST email address? Okay, we have. I just sent it. You will receive this. Thank you, Putala, for joining today. Go through the notes. Try to understand this because lectures are just support only. Okay. So understanding is totally based on your interest and your dedication. So it's your total responsibility. So go through your previous videos, previous notes, all and try to become well versed in thermodynamics. If you can be well versed in thermodynamics, you will be done, the country will be done. Okay? This is extremely important subject. And I'm assigned for that and I'm trying my best. So there are necessary things for us to learn. So these are somehow we have to learn and we cannot avoid. So there is no such thing as easy parts or difficult things in thermodynamics. All important. Okay. Forget easiness or difficulties. Just learn the subject. Okay. You will be very successful. And that is what we also need. Okay. It's very important. So try to feel good about the subject. Extremely important. So need your support with a great dedication for the subject, not for me, but for you to learn. Okay. And the subject is not for memorizing. This is for understanding. Okay. So don't expect your memory to answer questions in the exam. No such questions will be there for you to answer based on memories. But based on understanding, yes, you can earn some good scores. But this is not about earning the scores or the good marks, but this is more than that. Okay. And for mechatronics and BST students, thermodynamics, this is your first and the last. But for manufacturing, they have applied thermodynamics as well. But make sure everyone, this is the basics. So basics, but somehow we should have some practical sense of this. That's why the learning approach in thermodynamics is a blend of practicality and theoretical aspects. Actually, there are no such thing as theoretical aspects. All connected practical in thermodynamics. So have a good practical sense, connect this with your theories and analysis, you will be done. Okay. Not just for the exams, but for utilizing your knowledge. Okay. And a lot of thermodynamics hidden knowledge is there in the nature. So you have the fortune to recognize this. So let's start with this subject so that you can learn those unlearned things and unnoticed things as well. So future is with you. So knowledge is very important. I mean, the useful knowledge is very important. So please think about this and learn the subject in very meaningful ways. Okay. So my contribution is limited because thermodynamics we can share, but learning is totally with you. Okay. So let me stop the class today. Good luck to you and take care all of you. And see you next week. Same time, and also we will plan for some extra sessions in the weekends. So later we will discuss that, and you will receive some exercises from Google Classroom. Make sure you have joined the Google Classroom. Okay. Thank you then. Okay. See you next week. Bye, Bhutana. Bye. Take care.
Thank you, sir.
Thank you, sir.
Thank you, Bhutana. Take care, all of you. Right?
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay. Thank you, Bhutana.